Hello, everybody. Today we're going to be talking about cascades and an introduction to distillation columns. We're just going to be continuing where we left off and moving on from flash drums. Okay, so the first thing I want to talk about are the limitations that flash drums have. So they're not very efficient at splitting materials or splitting mixtures unless you're talking about salt water. When you need a higher purity of product that is desired, you're going to need an alternative process. One thing that we can imagine is, what if we take multiple flash drums and set them up in series? So if we look at what we have here, we have one flash drum and we take the vapor. So if we have this flash drum and take the vapor from that and put it through a condenser, some of the vapor is going to condense into liquid, and then we flash that liquid into the second drum and we continue on the separation process further. So let's assume for this process that the vapor in the first drum completely condenses, so we have a liquid. So this is going to be a completely liquid process, and it's going to go through a flash throttle valve again, and we're just going to repeat the process, but with a pure substance than what we had over here. So when we do that, we can then conceptualize what happens to the final product. So for this, let's assume that the first feed was Z is equal to 0.3, and that both of the drums are able to achieve the maximum vapor composition possible. We went over that in, I believe, Lecture 2 and Lecture 3. And we're going to say that the vapor from one is condensed fully to a liquid and then flashed again. So first, let's look at drum 1 right here. If we look at drum 1 and we look at this equilibrium line, let's assume that it's the liquid within this vessel follows this equilibrium curve. We draw our y equals x line. What we're going to do is, in order to figure out what is the composition of the first drum, we would go to z equals 0.3, about right there. And since I said that we're assuming that it is the maximum vapor composition possible, we would go all the way up here and right there. So from drum 1, if we assume that we're achieving the maximum concentration of vapor, which is unrealistic because again the slope is infinity, then we would get that the y component, so we would say y1 is then equal to approximately 0.66, so 0.66. Okay, then once that gets condensed through here, it then turns from a y1 to z2, which is also equal to 0.66. So if we're taking the vapor here and fully condensing it, it's not going to change the composition, it's still going to be 0.66. So then what we would have to do here is go to 0.66 on our diagram, which is about here, and then go up again as well. So we would get that if we're assuming again that the highest composition of vapor separation, this would be approximately 0.85. So then we'd get that our y2 is approximately 0.85. What you can also do from this point here, since we know that it's this y composition here, and we're condensing it fully to a liquid, all we can do is go straight this way, and you notice that we also hit that same mark. Okay, that's going to be something we're going to be doing a lot in the coming chapters, and that is essentially the McCabe-Thiele diagram for distillation columns, but we'll get there. This is unrealistic, however, because we're not going to be getting a slope of infinity for separation. Something that we'd get is much more similar to this right here, which I have in yellow. So if I had here in yellow where we have an actual slope given, we would say that from our z of 0.3, we'd go here. The first drum separation would be there. We'd go all the way to the right, and then our second separation would be here. So something that's more practical would be somewhere about a final separation of approximately 0.69 or something like that. Okay, so that's a process that we can do to achieve a further degree of separation, which is just using flash drums in series. And so what we can do is we can take these flash drums and we can connect them into what's called a cascade. Okay, so a cascade is just going to be a collection of flash drums put together in series, where you're hopefully able to achieve, or you are able to achieve, a much more concentrated product at the end. So each flash drum, remember we talked about previously, is going to be its own equilibrium stage. So what we're doing by adding all of these flash drums is we are essentially increasing the number of equilibrium stages. By increasing the number of drums and incorporating the liquid product as well, we develop what is called a cascade. I said that. It's just when you have multiple flash drums together. These cascades can have various arrangements. They can have what's called co-flow, counterflow, and cross-flow, which we'll talk about in the coming slides. So the figure on the right is a very basic model, but what it's going to do is it's going to create a gradient effect. So as far as gases, this Y1 concentration would be of a higher purity than this gas concentration would be here, and this one would be the lowest gas concentration. So what you're getting here is you're not getting a lot of high purity products, you're getting a gradient of products here. And I kind of illustrate that right here, where the difference in concentration is not significant for the majority for these streams right here. One thing to note too is that the concentration of our feed, so if we look at this concentration, that's going to be very similar to our concentration here. The reason why we're doing that is we're taking a feed liquid, we're flashing it, we're condensing it, and then we're flashing it again, and we're getting that same liquid. So we're going from liquid to vapor to liquid to flashing again, back to liquid. So in that process, you're essentially doing the same thing twice. You're kind of repeating yourself. You're not really achieving much separation. So these are going to be approximately similar concentrations, so they're pretty useless. So in order to improve impurity and to get more useful products, what we want to do is create what's called a countercurrent cascade. So when a stream is condensed once and partially vaporized once, it has a similar concentration to the previous drum. So all that is just to say is that these are not very useful. But they are useful in other ways, because what we can do is say that if L1 has a similar concentration to V3, because again, I was saying this is similar, then what we can do is we can say, well, if these are similar, V3 and L1, why don't we take L1 and just put it back into this second drum? Because if we take it into the second drum, if we're saying that these concentrations are similar, then we can just add more feed into this drum instead of trying to pull it out. And so when we do that, we end up getting this result over here. So the resulting cascade is what's called a counter current cascade. And it's pretty easy to visualize that. You have vapor coming up this way, and you have liquid coming down this way. There is going to be some examples where you can have a cascade where, for these, you can begin to start imagining them as equilibrium stages if you want, but you can have a counter or a co-current cascade where you have a liquid moving in the same direction. You can also have cross-current cascades where you have current coming this way, and then you have some solvent coming this way. That's something we'll talk about later when we are talking about different types of separation techniques. But for now, we're going to be describing how we get to the distillation column from flash drums. So you can see here from the new diagram that we're only collecting liquids at the bottom and vapor at the top and feed here. So we essentially only have one flow into the system and two flows out, as opposed to the multiple flows that we have over here on the left side. However, notice here that there's flashing. This requires different pressures. So for all the previous drums that I told you, the previous configurations for cascades, these are all flat. If we're assuming these are flash drums, they have to operate at different pressures. So the pressures have to be such that they are accommodating for the vapor pressure of the higher concentration of the most volatile component. So your P1 would be greater and your P2 would be less. So a P1, at our drum 1, we would have P1, which is greater than P2, which is greater than P3, and so forth. And that's because you have a higher concentration of your most volatile component up here. So your most volatile component is the one that wants to have a higher vapor pressure. So it wants to boil off faster. So you need to have a higher pressure so that it prevents boiling off. So you would essentially get an increase in pressure this way. That's going to take a lot of compressors, very costly. So we don't want to have different pressures. So it's preferred to operate at one constant pressure and to just allow the temperatures to vary. So as a result, the temperatures would vary in such a way that the higher temperature would be at the bottom and the lower temperature at the top. This has to do a lot with boiling points. So for the sake of most of visualizing, we're going to talk about ethanol and water. So if we imagine water boils at 100 C, ethanol is at a significantly lower boiling point. So this temperature up here at the top can be lower than this temperature down here at the bottom, because if we have mostly water here and mostly ethanol up here, then we would have this to be at something closer to 100 degrees, the boiling point of water, and this would have to be closer to the boiling point of whatever ethanol is. So the temperature is going to vary across the column, where the higher temperature is going to be at the bottom and the lower temperature is going to be at the top. Okay? And something to note, that most volatile component is just going to be abbreviated MVC. So in order to do this, we would have to employ some type of heat exchanger. So we go from this configuration, which requires different pressures, to this configuration, which requires now heat exchangers interacting between each stream, as well as now we have a constant pressure throughout the entirety of each of these drums. So you'll see here that starting to look a little bit better. You have vapor coming up, going through a heat exchanger, and liquid coming down, going through a heat exchanger. Okay? Reflux and boil up. So in order to better control the flow rates, so for this process, the liquid flow and the vapor flow between all these stages and overall is going to vary. So in order to better control the flow rates, what we would want to do is we would want to take some of the vapor and put it back into here. So if we condense some of this vapor out and turn it into liquid and put it back into the drum, we can get a better control of our overall flow rates. Same thing for our bottom here. If we have some liquid, boil it up and send it back up as vapor, we can create a better degree of separation. So what we do and how we do that is we add two heat exchangers, one at the top and one at the bottom. So this is the new configuration. There's our heat exchanger there and our heat exchanger there. This is going to boil up some of the liquid and make it go into vapor. This is going to condense some of the vapor and, this is going to boil up some of the liquid and send it into vapor up the stream, up the column, where this is going to condense some of the vapor into liquid and send it down into the column. Okay? We call this the condenser. Okay? At the bottom, that's going to be the reboiler. What you can do is you can vary the duty or the energy required on either one of these, which will vary the amount of reflux, which is L0, that's going to be our reflux, or our boil up, which we call V6. Depending on how many number of stages we have, this can be just Vm, right? And for the sake of this example in this diagram, we're going to assume 6 equilibrium stages. This will also affect the product flow rates. So a little bit of notation here. We have L0 because it's coming from the 0th stage. There's no stage above it, so that's why we call it L0. This is L1 because it's coming from the first stage. This is V2 because it's coming from the second. So as far as notation and how we're labeling, we label the streams based off of where they are coming from, not where they are going. That's why even though there's 5 stages here, this is V6 because it's coming from some imaginary or non-existent stage V6 down here. Okay, what we're going to say is now at the top we have our products, which are our distillate, our D for distillate, and our B for bottoms. So if I say calculate the distillate, it's going to be D. If I say calculate the bottoms, it's going to be B here on the bottom. It's going to be what's coming out from the bottom of the column. Here again, we're going to have high purity of our most volatile component. It's going to be high here versus our most volatile component here is going to be very low. So what we can do is we can get rid of these heat exchangers and incorporate so we can get rid of these intermediate heat exchangers and have all of the energy being provided by just one condenser and one reboiler. And we get this new configuration here. And we have that the required partial condensation and vaporization of the streams are accomplished by the same heat exchanger. So we just say if we have one heat exchanger here, or if we imagine it as one heat exchanger, we can get all the heat we need from the corresponding streams. So we have vapor coming up that can act as a heater to cool or to heat up this liquid as it's coming down. So there's heat exchange going on between these streams as they're passing by each other. So if we look at, like I have right here, L2 and V3, L2, V3, they're going to interact with each other, and the liquid stream will partially condense the vapor stream, and the vapor stream will partially vaporize the liquid stream. Exactly what I said, where we're going to have each stream is going to exchange heat with the other to either cool down or heat up the other stream. So another assumption that we assume here is that since the heat of vaporization per mole is approximately constant, what we say is that 1 mole of liquid will vaporize 1 mole being condensed, so that we'll have the same amount of flow rates. So if we have 1 mole of vapor being condensed, we're also going to have 1 mole of liquid being vaporized. So again, that's going to allow for the flow rates between the columns to be constant, which is going to be an important assumption in next class session. So that brings us to our distillation column. So what does the distillation column look like? Well, it looks like a column like this, a very large drum, where we have these what are now called equilibrium plates, which are right here. These equilibrium plates allow for the heat exchange to happen between the vapor and the liquid. So we're going to further simplify this by building the entire system into one column instead of a series of individual stages. So you can see these as you're passing by Marathon. They have a bunch of distillation columns there. What we're doing is we're just taking all these equilibrium stages and putting them into one vessel that's at the same pressure. The intermediate heat exchange can be done very efficiently with L and V in direct contact with each other. It's very simple and very cheap. The highly concentrated, most volatile component is in the distillate, which I mentioned. And it works because every time we vaporize material, the more volatile component tends to concentrate in the vapor. Because again, most volatile component is going to have a higher vapor pressure. So it's going to want to prefer to be in the gaseous state than it will be in the liquid state. As the decreases in alpha results in increasing difficulty, I think that's pretty obvious because we've been talking about relative volatility. As we approach 1, we approach azeotropes, and as we do that, we no longer are able to get any separation. One thing to note is that an azeotrope can occur at either the bottom of the column or at the top of the column. So it just depends on the mixtures that you're trying to separate where the azeotrope can occur. A possible concern is that you can have chemical reactions taking place, or you can have decomposition at elevated temperatures. So if you're trying to distillate chemicals that decompose, that undergo a decomposition reaction, that's something that you're going to have to be aware of. Or in order to solve this, you can just simply operate the column at a lower temperature, or you can use a vacuum or a steam distillation instead. One thing to note is that there's going to be different sections within the column. So within the distillation column, you're going to have what is called the enriching or the rectifying section at the top. That's where we're getting a lot of the gas is going to be filled with high MVC, versus the stripping section, which is where we're getting rid of a lot of the MVC. So in industry, distillation is by far the most common separation process. So when we talk about different like separation processes and techniques that chemical engineers use, distillation accounts for approximately 90 to 95% of all separation processes done. So it's easily the most common, most familiar, and most studied. So in the United States, there are over 40,000 distillation columns being used. We have evidence of distillation columns being used as far back as the 1st century, and there's evidence that by the 11th century it was used to ferment alcoholic beverages in Italy. In the 1980s, it was estimated that 2/3 of all distillation energy in the United States was a result of crude oil refinement. So again, here, if we're looking at how we get gasoline, we take crude oil, we put it into a distillation column, very simplified figure here. It's a lot more complex. And then we get clean gas, we get sulfur, diesel, waxes, and so forth. Okay. Distillation equipment, what does it look like? So here is a bunch of different distillation equipment. This is going to be what is inside of the distillation column. So that's going to be like the trays or the stages, the equilibrium trays, which you can imagine here from this diagram is through these little slots, you're going to have gas coming up, And as the gas is coming up, the liquid's falling down. And there's going to be intimate contact with each other such that you're getting that heat exchange that we talked about previously. So here you would get some frothy, bubbly mixture where some of the gas is getting entrapped by the liquid, some of the liquid is getting pulled up with the gas and being vaporized, and you get that intimate exchange, that long exchange, such that you have efficient heat transfer, and you could assume that each liquid and each vapor leaving the stage is in equilibrium with each other. So that's another thing I want to point out that's important. So the vapor leaving this stream, leaving this tray, and the liquid leaving that tray are in equilibrium with each other. The vapor coming into this and the liquid coming down do not really have a relationship together. Okay? It's only the vapor leaving and the liquid leaving the trays that are in equilibrium with each other, and where you can get the components of those from the vapor-liquid equilibrium diagram. So here you have a little bit of a pooling. So you can see from this picture, from this diagram, that there is a little lip here. You can see that here. There's also this lip, if you can see. That's there to pull up some of the liquid. So the whole point of that is that you don't have just the liquid straight going and falling. The liquid has to come and pull up a little bit, and you have to create a little bit of pool of liquid before it can then start going down. So this is just a little bit of nomenclature. You have the inlet region. So if you can imagine, here's where the liquid's going to fall into here. It then comes into here. Once it builds enough, it comes back down, and then it enters the other stage, and it goes in the opposite direction, like a snake effect. You have the deck, which is this section. The downcomer is the liquid that's going to be leaving, and then you have the inlet region. Here's a bigger distillation column. Same process. You again have liquid coming down here, and then this goes down this way, and then you still have that lip that I was talking about. This is an industrial distillation column that we have right here. That's what they look like when you see them out in the field. And this is just inside with a couple of trays stacked together. You can see that it's alternating. The downcomer would be here. I think it would be there. Yeah, I think you have a good idea of what they look like. Design considerations. So as with flash drums, there's typically an adiabatic flash through a valve prior to the distillation. So what I mean that is you usually have a valve before you enter the distillation column, but we're going to be disregarding that because it is going to be adiabatic, so we're not going to consider any of the temperature or heat, or we're not going to be considering any of the heat effects in that process. It's going to be very similar to the flash drums. So when you're operating a column and pressure increases, so does the temperature. So if you're looking at operating a distillation column at an elevated pressure, you're going to also have to elevate the temperature as well. For any given feed, the degree of separation and pressure, for any given feed and degree of separation and pressure, there exists an infinite number of theoretical stages. Conversely, there also exists a minimum number of stages that correspond to infinite reflux. So when I say infinite reflux, when I was talking about the column, let's draw a column here. So what you would likely draw a column, which I have over here in the next slide, reflux. So remember, this is your reflux, your L0. When you completely close that off and you're sending all of it back into the column, that's when you have infinite reflux. Then there is also when you have an infinite number of theoretical stages, which we'll talk about on Monday. So the spacing between the trays can vary between 2 inches and 48 inches. However, typically you'll see that it's about 2 feet, maybe 3 feet is about the industry standard. So that's going to result in a cap of about 300 feet. Usually distillation columns avoid getting higher than 300 feet because at that point it's just too tall. There's a lot of other concerns. So keep the column, when you're designing columns, you have to take a little bit of math to know that there's 2 feet between spacing. How many equilibrium trays am I going to need? Let's say you need 10 equilibrium trays and each one is 2 feet spaced apart. Then you would end up saying that it's about 20 feet or something like that. Okay. So just something to know. Flow rates can determine which region or phase, regimen or phase the liquid is on the tray. So how I showed you all what the equilibrium trays look like in the previous slide, the liquid can have different appearances. So it can have a very foamy, very frothy, different appearances based off of the gas flow rate, so the boil up that you are sending into the column. So there's essentially 4 different regions. There's a bubble regimen, which is when the liquid is close to being a stagnant pool with distinct bubbles rising through it. So this is when the gas flow rate is too low. You have the foaming region, which is the liquid phase is continuous and has fairly distinct bubbles rapidly rising through it. Then you have the froth regimen, which is liquid is continuous and has a large pulsating voids of vapor rapidly passing through it. This is going to be what is most used in commercial operations. So these distillation columns are going to have the liquid not being a stagnant pool or a foam. They're going to be in a frothy region where you can get the degree of intimate contact with the gas needed to achieve equilibrium. There's a spray regimen, which is when the vapor is too high and you start to get liquid droplets are going to be going up. It gets entrained with the vapor and gets brought up with it. Okay. Some specifications for the distillation column. So in the design or operation of a distillation column, a number of variables must be specified. The usually specified variables is the column pressure, which is going to set the equilibrium data, because equilibrium data, all those curves that we see, are the temperature varies, but these are all set at a defined pressure. So whatever the column is going to operate is where you need to get the equilibrium information that corresponds to that column, that pressure. Feed composition is going to be a variable that you're going to be setting or given. The feed flow rate, the feed temperature, or the feed enthalpy, or the feed quality. Or you can also specify the temperature or enthalpy of the reflux liquid. The usual reflux condition is set as a saturated liquid reflux. So I'll talk more about that in a couple slides. So heuristics that engineers usually try to meet when they're designing distillation columns. So we don't really want to use vacuum distillation columns because they're very expensive. Typically, we want to stay at a bar or greater, at 1 bar or greater. It costs much less to increase or operate a column between 1 and 7 bar than it does to operate outside of that range, either at a vacuum or at above 7 bar. Above 7 bar, we start getting a lot of safety concerns because of the elevated pressure. The condenser pressure should be set so that cooling water can be used in the condenser. So if you're at a plant, there's just cooling water. You can just think of it like tap water. You want to make sure that the condenser is operating such that the tap water can be used. So if you just have water flowing through a plant, that you can use that to cool down the condenser. So assuming that the change in temperature in the heat exchanger is about 5 degrees, the minimum temperature of the condenser will typically range from about 3 to 50 degrees Celsius, depending on the location. The reboiler pressure should be set so that the available steam or other hot utility can be used for heating. I had talked previously, I think it was last week, with how we use steam to heat. We take steam at 100 C, typically at a plant, or just above 100 C, and we then use that steam to heat up another process, which causes the steam to condense into liquid. So that's just reiterating that point that I had said, where you want to use whatever available steam you have so that you can use that to heat the reboiler. So you want the reboiler temperature of the bottoms to be approximately 5 degrees below the steam temperature. Note that reboiler and condenser pressures are not independent, but are related by the pressure drop in the column. So you'll usually get about 1/10 of a PSI change per stage for the column with pressure at greater than 1 bar. So you do get pressure differential across the height of the column. For the sake of this class, we're going to assume that the entire column is just going to be at a specific pressure, but just know that you are getting a pressure differential across the column. So reflux ratio and optimum feed. So we're going to define reflux ratio as this R is equal to L naught over D. So if we're looking at here, our reflux ratio is how much are we sending back to the column versus how much are we getting that, are we pulling out? So remember when I said something about infinite reflux ratio, infinite R, that's when we are setting no more D, everything is going back into the column, this becomes 0, and we get infinity. That's just what that is. Optimum feed location is going to be defined as the location in the column where it results in the minimum number of equilibrium trays. So you can put the feed into here, you can put the feed into here, you can put the feed into this tray, you can put the feed into any column equilibrium tray, but you just want to put it in the tray that results in the minimum number of stages used. That's going to result in the most efficient tray location. Okay. So what are you going to have to determine? Typically, you'll be asked to find the distillate and the bottom flow rates. So you would likely be given feed and feed flow rate and feed compositions, and you'd have to find distillate and bottoms. This would be through your mass balance equations. The heating and cooling requirements in the reboiler and the condenser, the number of stages required and the optimum feed stage location, the required column diameter, maybe. Don't know if I'll be asking that. I probably won't, but just know that that's something that you would have to find after you figure out all these variables. So these may vary, but understanding the concept behind how a column works will allow you to solve just about any problem. Review, you can look at section 3.3 in WinCat for more details. Also, please note that this slideshow is on Canvas, and within the notes section of the PowerPoint, I have a bunch of different words and details. Please be sure whenever you're looking at any of my slides that you look at that. I'll show you what they look like at the end. So drawing a distillation column. So when you're doing your homework or whatever it is, your exam quiz, here's the basic minimum that you're going to need to do for drawing a distillation column. It's essentially just an arrow into a box where this comes out into a condenser and it comes down and it splits into the reflux and the distillate. You can draw a reboiler in two different ways. You can draw a reboiler this way, or you can draw a reboiler this way as another circular heat exchanger. It doesn't really matter. Sometimes it does, which I'll show you in the next slide. But essentially, this is just going to be the basics on how to draw a distillation column. Also, too, you would want to make sure you write out your Z. You know, if you have Z1 is equal to whatever, Z2 is equal to whatever, and so forth. Same thing with now these are no longer Y's. These are D's or X's because this is liquid because of the condenser. So because this is liquid, you would have XD, and here you would have XB. Okay. So drawing the types of condensers and reboilers that we're going to encounter. So you have a total condenser. For a total condenser, just this means that all the gas goes to liquid. Okay, so we're saying for a total condenser, what we're doing is we're taking the vapor phase here and we're turning it into a liquid phase. There's a couple of things that can happen for a total condenser. You can actually condense the liquid below its saturation temperature. So let's take water, for example. If we're taking water, pure water, and we have vapor water at 150 degrees C. A condenser can condense this down to just below 100 or just at 100 C where it's liquid, or it can drop it down to 50 C. This would be subcooled liquid. Okay, so if it's a subcooled liquid, it would have to specify that, and it would have to tell you the temperature at which it comes out, or it wouldn't tell you the temperature, and you would have to figure out what the temperature is. So just know that a total condenser is going to cause all of it to condense into liquid, and it's going to go from vapor and completely into liquid. Similarly for a reboiler, it's just we're taking liquid and we're putting it into gas, into vapor. So here we would have liquid, and then from a total reboiler, we are sending all of it into the vapor phase. So then we would have all vapor. Just like the total condenser, you can have liquid, let's say water at 100 C, and you can boil it up to vapor at 100 C, or you can have vapor at 200 C. So a total reboiler can bring it up to the saturation temperature, or it can increase it past that. This is what it looks like for a total reboiler, or you can draw a total reboiler this way. Next, we have partial condensers and partial reboilers. These are much different than total condensers and total reboilers. So for these streams, for the previous total and partial, we have one stream coming out of each. And this stream can be split. So for distillation columns and a total condenser, this can be split into let's say you have your distillate, and then you have a separate stream going back into the column, which is your reflux. These are the same. They're the exact same composition. They're not the same flow rate. So if I say, so L naught doesn't necessarily have to equal D, but the compositions do. So if we look at X L naught is equal to XD. So the composition changes, the compositions are the same, the temperatures are the same. The only thing that we're changing are the flow rates because we're just splitting the stream. Same thing for a total reboiler, although total reboilers are not too popular or are not going to be too common, although I think there is one in your homework. What is going to be very common too is going to be a partial reboiler. So typically for a distillation column, you would have the total condenser at the top and then the partial reboiler at the bottom. So how do partial reboilers and condensers work? Well, they act as an equilibrium stage. They act as an equilibrium stage in such that this liquid coming in for a condenser, for a condenser, it's vapor. This vapor coming in, some of it is going to return as vapor, and some of it is going to come out as liquid. Same thing here. For a partial reboiler, we would have liquid coming in, you would have vapor coming out, and then you would have liquid also coming out as well. These vapor and liquid streams are in equilibrium with each other. So they are in VLE. It's going to be a key point to remember. Okay, so for partial reboilers and partial condensers, these actually act as equilibrium stages. So if I was to say how many equilibrium stages are required for a distillation column with a partial reboiler and a partial condenser, you would have the number of actual stages. And then if you had the partial stuff, whatever, then you would have 1, 2, 3, 4, 5. You would have 5 trays, but then you would also have these 2. So if I say equilibrium stages, so if I said how many equilibrium stages, it would be 7. If I said how many trays, it would be 5 because you have the 5 trays. But if this is a partial condenser and this is a partial reboiler, these act as equilibrium stages, so you would include those in the total count. Okay? And then here's also another way that you can draw a partial reboiler. It's the same effect. You have liquid coming in, you have liquid coming out, and then you have vapor. Okay? So I just want to iterate it one more time with the partial reboiler. If you have this, if I just call this Ln, and if this is going back as VB, and I say that this is XB, I guess this is V of n plus 1, because it's technically, if we're imagining that we have a distillation column with n number of stages, this liquid is coming from the nth stage, and this V is n plus 1 is vapor coming from an n plus 1 stage, which is your partial reboiler. One thing to note is that if this is Xn and this is Y n plus 1, and this from the bottoms is XB, Xn, Yn plus 1, and Xb are not equal. None of those are going to be equal to each other. None of these for a partial reboiler or for a partial condenser are going to be equal. Okay, moving on. External column balances. So the very simple, not too complicated. You're just going to create an envelope around the column. You're going to include the feed, you're going to include the distillate, and you're going to include the bottoms. You're also going to include, for the energy balance, the heat required from the condenser and the reboiler. So for binary systems, we don't have to do a stage-by-stage calculation. So stage-by-stage, I mean, if we're looking at this first stage, figuring out the components, then going down to the second stage, figuring out the components and so forth, what we can do is we can just do an overall. One thing I want to note is the labeling. That's pretty important. So when you are in the enriching column or above the feed, note how your V and your L are just written as V and L. Okay, the subscripts, I wouldn't worry too much about it. But you do have one starting from the top. So you have V and then you have L. Below the feed line, below where the feed gets entered, you have V bar and L bar. So V bar and L bar. That's to denote that this is below the feed line is your bars, okay? That's actually pretty important. You can also have a situation where you have two separate feeds. If you had a separate feed here, you would have that this would be V and L. Then between this region, you can have, you could say either V bar or L bar, or you can say, V prime and L prime. And then below this region here, again, you would have different labeling scheme. So you can either do V double bar, L double bar, or you can say V double prime or L double prime. I think I'll typically use the primes if we start for the bottom, but just know that it's just a way to denote that it's under the feed line or under which region of the column you're at. The reason why it's important to denote that is because the mass flow rates, when we start getting into internal balances, the mass flow rate is going to change and the slope is going to change within this region versus this region of the distillation column. So that means you'll end up having two separate operating lines, which we'll get into next week, or I'm sorry, on Wednesday. So the figure to the right shows a column with typical design problems specified. So everything that's circled is usually going to be something that's specified for a problem. Again, usual doesn't mean always or guaranteed. We assume that the column is going to be well insulated. So well insulated column just means that we're not getting any heat from the column other than the condenser and the reboiler. We also assume that there's a constant pressure throughout the column. I briefly talked about that as well. Mass balance. So the mass balance is pretty easy. You have F coming in, you have D coming out, and you have B coming out. Not too bad. Most volatile component balance is going to be the exact same that we did for flash drums. The only thing to note is that there are all X's now. You have XD and XB because with the condenser, we no longer have vapor. That's usual case. Again, if I was to say this was a partial condenser, then you would have liquid would be coming down this way, and then you would have a vapor distillate coming out because the partial condenser gives only partially condenses, so you'd be extracting the vapor. So your mass balance can be written in terms of FB plus D. Then you can say that your most volatile component, FZ, is equal to DXD plus BXB. If we would get that most likely feed's going to be given, most likely feed would be given, Z would be given, XD and XB would be given. So we can just solve for this and say, well, B is equal to F minus D. And if we plug that into here, we get that FZ is equal to DXD plus, this ends up being F minus D times XB. Distribute that and leaving just the D's on the inside, we get minus F XB is equal to DXD minus DXB. Factoring, doing all that factoring and dividing out, we can find that our distillate composition is just equal to F times Z minus XB over XD minus XB. Okay, so that's an equation that you can derive. It's not super hard, and you would be given all this stuff. So that's a equation that you can solve for figuring out your distillate flow rate as in terms of your Z composition, your Z flow rate, XB and XD. All right, you can also do the same for your B. And that would just be a simple matter of saying, well, distillate flow rate is equal to F minus B, and then repeating the process and just plugging in for D here instead of for B, and then factoring out. Okay. Energy balance equations. So similar to the flash drum, we have essentially just a control of our enthalpies coming in and coming out. So everything though is going to be a liquid, so we don't really have to worry about vapor. So we would have enthalpy coming in, enthalpy coming out, enthalpy coming out. Then we have duty of the condenser, and we have duty from the reboiler. And again, pretty simple. QC is condenser, QR is reboiler. Big note here, if the energy is removed, it will be negative. And that's because this equation is going to assume that all energy is treated as an input into the system, where the system is, again, your liquid, it's your mixture, it's your column. If you're putting energy into it, it's going to be positive. If you're removing energy, like the condenser does, then it's going to be negative. Okay? So typically, your reboiler will be positive, and your condenser will be negative. Enthalpies are functions of your Z compositions, temperatures, and pressures. Okay? Oh, I did not write this in. But essentially, it's going to be the exact same. Your HB is going to be equal to little hb, which is a function of xb. And it's going to be your temperature. And it's going to be a saturated liquid. And it's a saturated liquid because it's leaving the reboiler, which acts, again, as a equilibrium contact. Okay, so if it's an equilibrium contact, it's coming out as a saturated liquid. So the temperature doesn't necessarily matter that much because you'll know that it's based off of this composition, and you know that it's a partial reboiler, it's going to be a saturated liquid. You can just go to the boiling line or the saturated liquid line in a enthalpy chart and go from there and figure it out. Okay, moving on. So how to find Q over the reboiler. So let's kind of go back here for a second. When we're looking at the energy equation, we're going to get that this is, we'll have all the compositions. So we'll be able to find enthalpy of F, we'll be able to find enthalpy of D, distillate, and we'll be able to find our enthalpy of our bottoms. So we would have this, this, and this. So we would then need to figure out which one's the easiest to solve for. Is it our condenser or is it our reboiler? Now remember I said for the reboiler, which is usually a partial reboiler, and this is usually a total condenser. For the partial reboiler, the components coming in, the composition of the most volatile component are going to be different for each stream entering and leaving the reboiler. However, the components or the composition of the most volatile component is the same for the condenser. So if it's 0.9, it's going to be 0.9 here. So that makes the calculation simpler, and it kind of makes it preferred to go at about this spot here. We also have 3 streams interacting with our reboiler versus only 2 streams interacting, one in, one out, for our condenser. So that's why when we're choosing which one of these two to look at and analyze, we usually analyze the total condenser. If there's a total reboiler and a partial condenser, maybe we would consider looking at the total reboiler instead. So for finding the energy required from the reboiler, so the easiest way to solve for the reboiler energy is since it only changes phases and not composition. With the vapor going across the condenser, we know, again, what I said, where your composition of your most volatile component is going to remain unchanged throughout the phases. The only thing that's changing is your phase. And the splitter only allows for flow rate redistribution, not composition redistribution. So from there, we know if we're doing a envelope around the condenser, shown to the right, we have in equals out. So we have in coming is our V1, which is our vapor, leaving our topmost stream, our topmost equilibrium tray, is equal to our distillate coming out plus our reflux going back in. If we're looking at the energy balance, it's the enthalpy coming in, which is our vapor. Enthalpy coming in, or work being done onto the system, is our reboiler. And then we have distillate enthalpy coming out, and we have liquid reflux enthalpy coming out of the envelope as well. Okay, so from there, we're able to figure out what is our heat of, So we can just say that QR, or heat of the reboiler, is equal to distillate HD plus L naught H naught minus V1 H1. Okay, we know that our distillate enthalpies are going to be the same because these are the same composition of liquid. Our L and our D are the same composition and they're the same temperature. So we know then that our HD is equal to H naught. So we can just make that in terms of HD. So this would be equal to DHD, or this would be equal to just D plus L naught times our HD minus V1 H1. And then right here, we have that we can plug into there and say this can further simplify. We could say V1 times HD, little hd, which is liquid enthalpy, minus V1 H1. And again, we could just simplify that further to get our overall heat from the reboiler is going to be equal to V1, or vapor, whatever vapor is coming into the system, vapor times HD minus big H1. Okay, so again, this is the enthalpy of the distillate, and this is the enthalpy of the vapor leaving the distillation column right here. Note that it's always going to be negative because the enthalpy for a gas is always going to be greater than the enthalpy for a liquid. So this is going to result in a negative value. Okay, that's something to know. The equation right here, kind of a big one. All right. So let's go through an example problem. I was hoping to have you all do this in class, but I guess I'll just work through it, or at least most of it for you all here. So if we have a steady state countercurrent staged equilibrium distillation column being used to separate water and ethanol, we have that the feed is 30 weight percent, 70 weight percent water. It's at that degrees. So there's all the information. I'll let you all read it. Let me make this smaller. Chill. Okay, make it smaller so that I can work on it here. Also, when I was talking about notes, right here is what I'm talking about in this section. You'll see when you're going through slides, if you can't make it to class, I'll put most of the notes that I either talk about or something that I want to make note about will be here. Some of them don't have them, but yeah. Okay, so let's work through this example problem. So we have a steady state countercurrent staged distillation column is to be used to separate ethanol from water. Let's go with purple. So let's just draw our distillation column, right? So we have our feed. Okay, so we have a countercurrent stage distillation column. The feed is 30% ethanol. So right there, I'm going to say that Z is equal to 0.3. We have that our temperature is at 40 C. We have our flow rate, 10,000. Column pressure is at 1. The reflux is returned as a saturated liquid. And the reflux ratio, L over D, is equal to 3. Saturated liquid, that'll come in handy later. We desire a bottom composition of X 0.05. And a distillate composition, XD, being equal to 0.8. The system has a total condenser and a partial reboiler. Find dB, so pretty much find the flow rates, find the duty about each of the heat exchangers. So not too bad. We're going to just start off with our overall. F is equal to D plus B. And we're going to start off with our moles volatile component. Okay. Using the equation that I had showed you previously, we can end up solving for D and getting that D is equal to F Z minus, I think it was XB over XD minus XB. And then again, you can always just solve. So just to double check, I'm going to say F minus B, plugging that, or no, I want to do the other way. F minus D, plugging that into here gives me F Z is equal to DX D plus fxb minus dxb. Moving and factoring, I end up getting that is f and z minus xb, which I have here. And then I get xz minus xb, which I have here, and a d. Okay, so that's correct. So it's just a simple matter of plugging it in now. So d then is equal to 10,000 times z is 0.3 minus 0.05 over 0.8 minus 0.05. From that, we get that our distillate flow rate is going to be equal to 3,333, and the units are going to be kg per hour. And if we just plug that into here, we get that our bottom flow rate is just going to be 10,000 minus that, so it looks like it's going to be 6,667 kg per hour. Cool, not too bad, right? So now figuring out what it is for our enthalpy equation. So remember, for our enthalpy equation, let's see, do that in a different color. What was our enthalpy equation? We can just derive it. So in and out. So for enthalpies, we have, it's going to be our feed flow rate times our enthalpy, H of F, plus the work from the condenser and the work from the boiler. It's going to be equal to D times HD minus plus B times HB. Enthalpy's in, enthalpy's out. Okay. Again, we're going to end up needing all these H's. So let's go to the enthalpy diagram. And we have our we have the information for all these. So let's go to the diagram that I have over here. The information given was that our feed is at Z is equal to 0.3 and our temperature is equal to 40. We have that our distillate was XD is equal to 0.8, and we had that it is a saturated liquid. For our bottoms, we have our XB is equal to 0.05, and we had there that it was, I believe, also, since it's a partial reboiler, we assume that is a saturated liquid as well, since it's a partial reboiler. So how to find these? So the first thing we're going to do is we're going to go here to our feed, which corresponds to 0.3. Right here, we just start here at 0.3, and it tells us that it's at 40, so easy enough, we just go straight to the 40 line. Right there. And once we go to the 40 line, right here, you see this 20 corresponds to that line, this 20 corresponds to this. So for 40, it's this. We just go straight across, don't follow the line. Something like that. So we can then say that our enthalpy from our feed is approximately equal to, I guess we can say about 30 kcal per kilogram. Right, yeah, because that's about 50. Okay, and then for our distillate and for our saturated liquid, we go to XD. For XD, we go right here at 0.8, and we know that's a saturated liquid. So we're going to go to the saturated liquid line. So from there, we're going to go up to there. Okay, up to there, and then we go across. Looks like half is about here-ish, so we can call that about 60, I guess. So we can say our enthalpy from our distillate is approximately equal to 60 kcal per kilogram. And then for our bottoms, so for our bottoms, it's 0.05, so it's going to be about here. Again, going to the saturated liquid line, about there. Corresponds to, I don't know, you can call that 95, 90, 95 or 90, let's say 90. Whoop. So then our HB, approximately 90 kcal per kilogram. Okay, that's all it is. So we can then take this information back. So we have 30, 60, and 90. So this is 30, then we have 60, and then we have 90. So all that's needed then We have everything except for our heat of the boiler and heat of the condenser. Again, we said it was easier to do the heat from the condenser, so let's do that. Using the equation, we know that the heat of our condenser is just equal to our vapor flow rate. It's going to be equal to our vapor flow rate times our HD minus H, big HD. Again, same composition, so it's just whether or not you're going between saturated vapor or you're going to saturated liquid. And we need our V, so that's our V1. That's where our reflux ratio comes into play right here. Okay, remember if we did a balance around the condenser, we have that V1 is equal to D plus L. We also know from our reflux ratio that L naught over D is equal to 3. Since we know D already from our work over here, we can just solve in terms. So we can say L naught is equal to 3D. Plugging that back into here, we can say that V1 then is just equal to D plus 3D, which is equal to 4 times our distillate flow rate. Okay, that's our V1. We can take that, plug it into here. So we know that the duty from our condenser is just going to be equal to 4D times the change in our enthalpy of D minus our enthalpy in gas phase. So we have our enthalpy of our D, it's right here, 60. So we can say that this is equal to 4 times our distillate flow rate is 3,333 times our distillate, which is 60, minus whatever our enthalpy is. So we know this is going to be saturated vapor. The reason we know it's saturated vapor is because this vapor is leaving this equilibrium tray. If it's leaving that equilibrium tray, liquid and vapor leaving an equilibrium tray leave at their saturation points. So it's going to leave at your saturation gas and at your saturation liquid. So all we would do here is go to our enthalpy diagram. We said it was 0.8. So here we're just going to 0.8. Instead of going to our liquid, we're going to go here to our vapor, saturated vapor line, and go all the way across. And we say it's about 330. Something like that. Looks good. So let's go back then. And say it's 6 minus 330. Do the math, and you end up getting a value for your condenser. Some number. I'm going to leave that to y'all. Then you take the value of your condenser, plug it into here. You have everything. You can solve for the duty from the reboiler and get your number and solve the problem. Yay! If you all have any questions, please feel free to reach out to me. I will be around. If there's anything that's unclear, I'm more than happy to address any problems. Okay? Have a good day, and I'll see you all on Wednesday.